So welcome back friends for another lecture on quantum field theory and quantum computation. We were looking at the Feynman propagator of the Dirac fields in the previous lecture. So in this lecture we'll continue, we stopped just before the defining the Feynman propagator. So we essentially did the ordinary propagator which is as alpha beta in terms of the d essentially, which is e power ipx minus y, essentially the integral of e power ipx minus y, and showed that we had a worry that whether the commutator of the field values essentially vanishes outside the light cone or not, the field operators essentially. So this commutator of the field operator doesn't vanish because it is the anti-commutator which vanishes essentially outside the light cone. Now, but then you will say because we argued a lot for the causality, but it turns out that in the fermionic case, what is more important are the bilinears, the fermionic bilinears, and these fermionic bilinears commutes outside the light cone. So they all vanish outside the light cone. The commutators of this fermionic bilinears always vanishes outside the loop. So the causality is really conserved essentially. Now we actually now move towards defining a properly the Feynman propagator for the Dirac fields, which is as you well know, time ordered and so on. So time ordered and well behaved essentially. So let's start with the Feynman propagator for the Dirac fields. Okay, so uh, one can define for the Feynman propagator. We need two things essentially. So let's start with the vacuum expectation values of. So let's start with the vacuum expectation values of psi alpha of x, psi beta bar of y 0, that is called integral d cube of p. We can actually compute this by using the mode expansion which has been introduced in the last class essentially. So 2 pi cube 1 by 2 p e pi bar p slash plus m alpha beta e power minus I p x minus y. Okay, so p slash plus m alpha beta comes from, as we have seen, it comes from taking the UU bar, the outer products essentially, and so this is what it gives you. And if you take the other one, psi beta bar alpha of y, psi alpha of x, the vacuum expectation now value p slash minus m gives you almost identical formula. Okay, this is plus e power I p x minus y essentially. So these, so this is psi bar essentially. So if you take the sum of these two, essentially you end up having the standard this thing. Now we define the the property. Now we define the time order product. That's Feynman propagator. Is defined, say, time order product as SF x minus y is equal to vacuum expectation value time order product psi of x psi bar y, this is equal to 0 psi bar, careful here, psi of x psi bar of y when x0 is greater than y0, and then it is 0 minus psi bar of y psi of x when y0 is greater than x0. Okay. Okay. Now there is a minus sign, you see, for psi bar of y and psi of x. Essentially, this minus sign is important. Okay, this minus sign is important because you have to make sure that uh, this anti-commutation psi bar psi should vanish always outside the light cone. Essentially, this the minus sign is to make sure is 0 for all x minus y whole square. So outside the light cone. Okay. Now, okay. Now this is again. This is also a 4 by 4 matrix, and we have computed this psi bar of each of these elements. We have computed above essentially. Okay, and we just have to make sure that there is a negative sign for y0 greater than x0 essentially, and that is important. Also, it's also essentially Lorentz invariance demands it. Right? And then causality follows essentially in some ways. Now it is instructive to look at the 4 by 4 or essentially the 4 momentum integral um, representation of the Feynman propagator. So how is this given? Now, okay, this is as a x minus y I d cube of or this d power 4 p 2 pi power 4 e power minus I p x minus y. So momenta p slash plus m by p square minus m square plus I epsilon. So the fermionic propagator has the form like this essentially. With a numerator, it has a numerator compared to the boson propagator. Okay, it has a numerator and the denominator looks very much similar like the boson propagator. Now we use the same thing, like we use the I epsilon prescription of the Feynman essentially, which we discussed in the boson propagator, which we discussed in several classes. So in the previous lectures, also in the relativistic quantum mechanics course, that this I epsilon prescription tells you which contour to take depending upon and the which in so making sure that the correct piece goes to infinity essentially, meaning the correct contour goes to, as you take the contour to goes to 0, the other piece vanishes essentially. That's the basic idea, that one of the thing vanishes. Okay, so this uh, the Feynman prescribed prescription I epsilon is exactly like in the case of uh, the bosonic propagator essentially. So you have the IPP minus 6, you choose the P0 contour in the P0 essentially, imaginary and real part essentially I epsilon will put the two poles essentially, and then accordingly you choose the contour in such a way that for negative P0 and the what do you call, the plus I epsilon and minus I epsilon, for both the things you choose different contours in such a way that the numerator goes to 0, essentially it vanishes, and so there is no contribution outside the light cone, essentially the causality is conserved and you end up having this nice picture. Now before going into the interaction picture, the interaction picture is exactly the same as we have done for the bosonic case. So the interaction picture just goes through uh, as in the fermionic case. So you can you have the Schwinger Dyson the Dyson series, and then you have the Dyson series, and then you impose this Wick's theorem, and then you do the contractions exactly the same way essentially, and you end up having the S matrix, which and the LSG combination rule to compute the S matrix elements essentially. Now the only complication, or uh, the only difference between the bosonic case and fermionic case is that, with only one major difference, that for the contractions and so on, so all the other things, that commutators are replaced by anti-commutations in the fermionic case. So this is the scalar case in which you have the commutators, and in the fermionic case these are replaced by the anti-commutation relations essentially. So you have things like say psi of x, psi of y contraction essentially. This is nothing but the time order product uh, psi of x, psi bar of y. Now this is should be equivalent to the normal order product. So that's what the Wick's theorem tells you, that now this should be equivalent to a normal order product. Essentially, this will be uh, uh, so this will be, and the difference between the time order product and the normal order product should be psi of x, psi of y, and then bar. So this is the normal, and the difference between the time order product and the normal order product is nothing but your SF Feynman propagator. Okay, um, which is given by this essentially. Now, one thing you should remember, that the normal ordering will always pick up a minus sign if you interchange this thing. So we have normal ordering of psi 1 psi 2 is equal to minus normal ordering of psi 2 psi 1. Okay, this, because you are interchanging two fermions, you will always pick up this minus sign essentially. Now with this understanding, that inside the time order product essentially, whatever n number of field operators we put in, all the commutators are replaced by anti-commutators for the fermionic case, time order products of fields what you have is that all the time out meaning commuters are replaced by um, uh, meaning essentially what it means is that all the scalars commute inside the time out product, whereas the fermions anti-commute, and we have relations because of this anti-commutation. You have relations like they pick up a minus sign, but this overall relation that the contraction psi bar or the fermionic the Feynman propagator of Dirac field equivalent to time out product minus the normal order product stays true, essentially stays true. So except for this part of the interchange of the fermions, will always pick up a minus sign, which will be important actually, as we will see later on for various other calculations also. Except for that part, the entire interaction picture which we studied uh, for the bosonic case. Okay, so the entire interaction picture which we studied for the bosonic case, like we started with the Dyson series, uh, H interaction, and Dyson series, and then S matrix, Bick's theorem, and then Feynman propagators. Okay, everything will follow. Essentially, everything will just automatically follow, uh, and LSD reduction formula. So where you only look at connected diagrams to calculate the S matrix elements essentially, and then connected diagrams, we throw them away, and then you can actually put all the particles on mass shell to compute the S matrix elements essentially. So the okay, so all this work, all this just follows through. Okay, so all this just follows through, and so we can now start playing examples with the various uh, what do you call various interacting theories essentially exam, and then we try to calculate S matrix elements according to them essentially. So let's start with the simplest example essentially. The simplest example would be consider a fermionic particle which is spin half, and a bosonic force mediator. Okay, so we know the bosonic, so let's put it this to be, will make the spins more accurate. Let's put it as spin 0, and this one let's look at as spin half. In this case, the spin okay, so let's write so what are the Lagrangians we need essentially? So we need the Lagrangians of essentially the Klein-Gordon field, which is for the spin 0, the Lagrangian of the Dirac field, which is for the spin half, and then you need an interaction term. So you have L is equal to L Klein-Gordon plus L Dirac plus L interaction. Okay, let's come to the L interaction in a second, but let's think about LKG. LKG we already know the Klein-Gordon equation. So it's half del mu phi del mu phi plus minus half mu square phi square. L Dirac is equal to I psi bar uh, del I del slash minus m psi. Okay, now this mu is the mass of the scalar, m is the mass of the fermion. Now let's think of writing an interaction term. Okay, L interaction. This I think we wrote it in the in one of the examples in the previous lectures essentially, but let's write it down. So what we need to write and what are the possible interaction terms you can write down. Now the interaction the Lagrangian should be 4-dimensional, which should be a Lorentz scalar. Okay, and it should be real. The Lagrangian should be Lorentz scalar, real, and okay, uh, and it should have properties which conserve as in unitarity and perturbativity and okay other things essentially. Okay, positivity of the amplitudes and so on, so essentially. So let's, but the basic thing is that it should be a Lorentz scalar and real. Now we are in 4 dimensions. Okay, and as we have seen in one of the previous classes, the dimension of psi is 3/2 and the dimension of phi is 1, mass dimension of psi is 2. So every term in the Lagrangian should be of mass dimension 4. So since L should have terms which are of mass dimension 4 such that the action is dimensionless essentially, that's the basic idea, such that at least in natural units. So given this, the interaction term you can write down is two fermions and a scalar. Okay, you see that it has mass dimension 4, and one combination you can think about is two you can also ask what about 5 power 4. Okay, that we have seen it already, such an interaction. So the possible interaction terms are essentially psi phi. Okay, that's, let's put a bar so that it becomes a Lorentz scalar. Then you can also have 5 power 4. Okay, A, this is B, and a pure psi bar, psi is just a mass term, so we cannot write anything like that. Okay, you need something which is the minimum thing beyond quadratic. The only term you can write down is a cubic or a quartic. We stop at quartic terms. Okay, anything other than like psi cube. Okay, psi cube would be what it will be. First of all, it's not Lorentz invariant, so you need to go to psi power 4. Psi power 4 is mass dimension 6, which is not really valid. So the only two terms which we can think are these two, and the first one is called Yukawa interactions. And this is the self interactions, which we have already seen essentially. Phi essentially of the scalar, self interactions of the scalar. So with this Li, okay, with this we have put a lambda to 4 factorial essentially. So Li, we will write it as, since we already seen the B part, okay, the Li gives me only psi bar psi phi. So with a coupling constant, essentially this is called a Yukawa coupling constant. So what we see already is that uh, the requirement of Lorentz invariance and that the okay, the dimension of the Lagrangian should be 4-dimensional and so on, so already puts a very strong constraint on the kind of interactions one can have. Essentially, you cannot have any arbitrary interactions you want. So the Lorentz invariance puts you very strong constraints essentially. Okay, with this now let's look at psi to psi couple interaction essentially. So let's consider scattering. Okay, so let's look at the initial and final states. So essentially, you have two psis. Essentially, we can think of two different spins, two different momenta. Before coming, we will write everything in terms of this uh, meaning what you call as Feynman diagrams in a second. Before coming into Feynman diagrams, let's have an um, uh, how the amplitude looks like. Essentially, we want to use, but we will try to proceed in the same way like what we did with the uh, writing the S matrix down essentially. Okay, like what we did with the bosonic case, except that now we had to take care of the spins essentially. So that's the point. So we are looking at essentially. So our initial state is, and we'll do the same thing with the Feynman diagrams in the next lecture. The initial state is I is equal to root 4 EP Q, say for example Q. Okay, let's put it as P and Q and R and S. The spins are and R and S, and essentially, okay. So BP bar S dagger, BQ bar R dagger acting on vacuum. Okay, so this is our initial state, and this will give me a state which has a spin P and momentum P and spin S, and another state with a momentum Q and a spin R. So this is your initial state, each representing psi. Okay, each one of there are two particles in the initial state. One is in P1, P and Q essentially. Now, if we exchange these two, you will get a minus sign. If you remember that essentially. So the final state, but it will not. Yeah, we will not worry about that essentially. So will be 4 EP EQ primes, same thing. So BP bar prime S dagger prime PQ bar prime R dagger prime, all acting on 0. So this gives a state which is P prime S prime Q bar prime R bar prime. So this is the final state essentially. Okay, good. Now we are now able to calculate the S matrix elements essentially, and the coupling is Y, right? Essentially, the coupling is Y. Remember, the coupling is Y. So you end up, so you can calculate the S matrix as F S minus 1 times I. So this will give me minus I lambda Y square by 2 integral d power 4 x1 d power 4 x2 time order product of psi bar of x1 psi of x1 phi of x1, okay, psi bar of product x2 psi of x2 phi of x2. Now this is slightly instructive to do it because you have, so there are two vertices essentially. We'll see this in Feynman diagram language essentially. Now you can think of the contractions essentially. We have to do the contractions. So we will do the time order. Okay. Now these are all in the interaction picture. Now you have to take into consideration all possible contractions essentially. Okay, and so you have the normal order of psi of x1, psi bar of x2, psi of x2, normal ordered, phi of x1, phi of x2. So this is the main contribution. This is the contraction between phi of x1 and phi of x2. Now phi of x1, phi of x2 contraction is nothing but, if you remember correct, okay, if you remember, this is nothing but your propagator. But then if you do the psi fields contraction, you have to be careful how the contraction works, okay, and it is slightly subtle essentially. Okay, okay, so let me do it once essentially. So for example, psi bar of x1, psi of x1, psi bar of x2, psi of x2, normal order BP, S dagger, BQ bar, R dagger spin is equal to d cube of k1 2 pi by 6 d cube of k2. What I am doing here, psi bar of x1 m is k1 psi bar of x2 dot un of k2. Okay, and this entire thing e power minus I k1. Now this is nothing but the term in the Dyson series, okay, minus k2 x2 by 4 ek1 ek2 bm k1 bn k2 bp s dagger bq s r dagger, all acting on vacuum. Now what is happening here is you are trying to every mode you are trying to expand one by one essentially, and so you are writing in the momentum space, so you end up having these kind of terms essentially. So you are seeing how the spinor indices are contracted. That's the main thing, is that this is just to show the complication involved with the spinor indices. So you have spinor, the alpha spinor, and then there's a un spinor corresponding to its two annihilation operators, and then you have the regular bs dagger and bq dagger for this x1 and x2 essentially. Okay, and how they contract, because you can think of them. Okay, now when you do the anti-commutation, now essentially when you do the anti-commuting, okay, B's and B daggers, then at the final step what you will end up is, okay, let me do, I won't do all the steps, let me write the final step essentially after carefully doing all that stuff. So you get your amplitude is equal to minus I y square, everything in terms of the spinor wave functions, p bar prime dot us of p bar and spinor product. This is a spinor u bar of r q bar by dot u of r q bar prime spinor product. This square brackets is the spinor brackets. Let me just emphasize this a little bit more. This square brackets are the spinor products. okay, by p prime minus p whole square minus mu square plus I epsilon. Now you see that uh, uh, this is mm, this is this. So this is the mass of this is the propagator of the scalar. So you have two amplitudes, and in fact it's as you see, this will be coming out as two diagrams, and the first one is from the first diagram and the second one is from the second diagram. Okay, so the second term is u bar of s prime p bar prime u bar of r q. Oh, okay, let me write the term 2 here downstairs, essentially minus term 2. Okay, y square. Term 2 is, okay, u bar of s prime p bar prime dot u bar u of r of q, and then u bar of r prime q bar prime dot u of s dot p whole divided by q prime minus p whole square minus mu square plus I epsilon. Now, the intermediate steps I have not done, okay, when we do this, but what we will see is that this entire thing, these two diagrams correspond to the two channels. We have seen these two channels when we are doing the Feynman 2 to 2 process. There is S channel, T channel and U channel, and you will see that this corresponds to, one of them corresponds to uh, okay, one of them corresponds to T channel, other corresponds to U channel, and so on. So essentially, so this is the amplitude. Okay, this is the amplitude. Okay, now instead of doing this entire procedure like systematically, uh, now doing it in this particular fashion, essentially like writing down, taking all possible contractions and all possible things and drawing, writing down this entire long thing, we will use the Feynman diagram approach. Okay, so this amplitude we will get it back, okay, in the next lecture by using Feynman diagram amplitudes essentially, techniques essentially. So this is the amplitude we got for psi psi to psi psi scattering. So in the next class, I have not fully done the derivation, but you can guess it will be complicated. Okay, doing this in this particular Dyson series way. Okay, but you can still get the answer essentially. In next class, we will do the same amplitude using Feynman diagram approach. Okay, so good. So the summary of this lecture is that uh, the interaction picture goes exactly in the same way as earlier, and as in the scalar field theory and everything. And we saw that the kind of interaction one can write down, the terms we can write down, are constrained by Lorentz invariance and the dimension of the interaction term. Okay, because which dimension you are, either in 4 dimension and so. And given this, we considered psi psi to psi psi scattering with the first example, and we tried to do it in the fashion of using the Wick's theorem and doing the Dyson series and computing the S matrix element from that essentially. And with this, we end up having the first amplitude here, and we will repeat the same amplitude using the Feynman diagram approach. in the next lecture. Okay, thank you very much. I'll stop here.